All right, hello people. So we're going to talk about topic 2.3 today, which is technological and cultural change. So we're going to start out by talking about the product lifecycle. Now this comes in five stages, and this is primarily regarding the product and its sales, so its interaction with the market. So this obviously starts with introduction, where the product is first launched, gets a little bit of publicity, maybe a little bit of an introduction to the market in terms of ads and marketing and that kind of thing. Um, and that will very often be in response to the pull of demand, so the need of that product in the market. Once the product's actually released, then we go through what's called growth. And the growth is essentially where the product gains a little bit of traction in the market, and there's an interest that begins to develop um, with its potential users. Then that further moves on to maturity, where we kind of see the product reach its peak potential or its peak performance, which most of the times will result in its maximum amount of sales and its maximum amount of desirability in terms of its use case. So what it's actually used for and how well it does in terms of market demand. Then we finally reach the latter end, which is going to be decline and then obviously replacement. These are often kind of approached together as the same sort of part of the process because replacement is very often followed right after the decline. We don't like to see a product crash and burn. We kind of like to see it just phase out and then we get replaced with something else. The product gets replaced with something else. So sales obviously begin to dip. Enough people have actually bought the product and owned the product, and so that big mass of sales that you normally get in growth and maturity isn't really available anymore. So very often, what tends to happen is a new version of the product is designed or is introduced to the market, maybe a V2 or a V3, which has better features or which has better functionality, which then makes the previous iterations somewhat obsolete. This is also where planned obsolescence comes in, where products are actually designed to fail or to become obsolete after a certain amount of time. And that's very often due to either intentional software updates or it might just be through the use of poorer quality materials or mechanisms that cause things to just physically break as well. Okay. Now we'll move on to the evolution of products. Now, evolution simply, similarly to the way it is in nature, it simply means the gradual change of something throughout time, often informed by need or by the requirement of some form of evolution, as you would see in nature over millions of years in animals and organisms and that sort of thing. But in products, it's more about making the product more usable, having it have better features, and obviously incorporating newer, more viable components. So it could be just smaller integrated circuits, or it could be better cameras, or it could be different types of lighting like LEDs as opposed to incandescent lights or fluorescent lights, things like that. Um, and you've got some examples here. So obviously the evolution of smartphones would be, better cameras, more powerful processors, better screens, larger screens. Obviously also like small 4K displays and stuff like that, as well as better memory and better materials. And the long-term development of this would have been, not even having smartphones in the first place, which yeah, we didn't have smartphones, more than let's say 15, 20 years ago. It was very much just a phone was a phone, and you just used it to call people and maybe play Snake and send text messages, and that was about it. So that evolution does span over quite a wide range of product, even just within phones in general. And then of course you've got televisions, which they've been getting slimmer. They're using better quality displays. They're also using OLED as opposed to LED or LCD. And then you also have curved screens now, and better dynamic range of image display and color display and stuff like that. And then, of course, with digital cameras, another example would be just the better pixel count. So, I mean, back in the day, even a 12 megapixel camera was considered a very, very high-end camera. But now a 12 megapixel camera, even on your phone, is considered to be a little bit on the lower end. So I mean, just based on that, you can kind of tell how quickly things have been developing. And then, of course, the introduction of digital sensors rather than optical sensors, which makes the whole process of actually physically taking photos a lot easier for processing and things like that. And then, of course, cameras also becoming waterproof, and even putting them on drones. As you can see now, you can buy a drone for a couple thousand Hong Kong dollars that has an amazing camera on it that you can use to film all sorts of things, and it's got optical stabilization and stuff like that. So I mean, you could essentially film a, a low budget film with a drone camera if you wanted to. Okay, so we're going to talk about socioeconomics. Socioeconomics is simply put how society and the economy interact to create particular instances or particular situations or circumstances, right? The understanding of socioeconomics enables us as designers to better recognize opportunities for further development in the products we make and the things that we design, and most importantly, the people who we design them for, right? Because socioeconomics fundamentally breaks down to different groups of people. Okay, so let's have a look at some examples. So an example of a socioeconomic position might be a recently married young couple who is looking to have children but hasn't quite had children yet. So, they're in that position in their life where they're trying to save money, but at the same time they're trying to develop a kind of fundamental framework for a family. So maybe they're looking at buying a house, or maybe they're looking at, setting themselves up in a way where they can be financially independent, but they're not quite there yet. Um, and so, they might be looking at products that are of good quality, but maybe not, at the very tip top of the scale, because obviously that's not within their price range. Another example might be students who move into university who are in a lower income bracket, and so obviously they're just trying to spend as little as possible but get as much as possible out of it. Um, and then another example could just be an aging population who would have been previously accepting of technology, but maybe limited by either physical limitations or financial limitations based on where in the world they are and what they do with their lives. Rationing is simply a concept whereby the resource of certain goods or commodities is limited, and that's due to a crisis of some kind. So that could be a natural disaster, it could be war. Very often, war and rationing come hand in hand. It could also be a natural shortage of materials or components. So in some cases, maybe very recently, you guys might be aware of a dip in availability of integrated circuits because of the lack of natural resources required to make them. So the price of integrated circuits have gone up, and as a result, we've seen an incredible shortage in the most basic things like laptops and graphics cards and stuff like that. Utility products are also related to war very often. In this case, most often they were post-Second World War based products, and they were usually rationed. There's some examples here. Utility products are essentially products that had a particular use of some kind, um, and they were created during the wartime for purpose. Basically, they were just sort of purpose built, and within that you obviously had variation, but for the most part they were designed for a specific use. So in this case, there's a chair, but it could also be other products like kitchenware and things like that, tables and all that sort of thing. Usually they would have been furniture though. Okay, so we're going to talk about some major developments in technology now. So first of all, you need to know a little bit about microelectronics. So the first development in microelectronics was the semiconductor in 1940s, and this was in the form of a transistor. A transistor is a small digital switch or a small electrical switch that basically allows for electricity to flow through it and then for it to have an on and off position, allowing electricity to basically dictate whether something had to happen or not, which basically then permitted sort of digital objects to be created or digital products to be created with some sort of small circuitry within them. Um, Now, the creation of these allowed for, in the long run, um, the use of integrated circuits, which is basically a small circuit board or a circuit board, which actually they used to be quite large, but now they've become small. um, filled with these transistors, which would then basically be used for making things like calculations or processing information and things like that. Okay. Um, some major developments in. All right, so we're going to look at some examples of major developments in tech here. So the sort of initial creation of transistors and integrated circuits developed really quickly. And there's a concept called Moore's law, which isn't really a law, but it's more of a concept or a theory that basically indicates that every 9 to 10 months, the amount of transistors that can fit within a certain size of a circuit board doubles. Now, of course, because it's doubling, it is expected to be exponential, but I mean, there will come a point at which that tapers off. There's sort of diminishing returns on that, but for the most part, it has been relatively accurate. Like the amount that you're able to store on your phone is an immense amount in comparison to what you would have been able to store in the similar amount of space, even 5, 10 years ago. So there's some examples on this page for you. I mean, a simple example would even just be, pencil sketching versus using a graphics tablet, because there was no graphics tablets before 10, 15 years ago, or maybe more than that. And the invention or the creation of these transistors and integrated circuits have allowed for the developments of iPads and graphics tablets, which we can now fit in our hand and give us so much more room and so much more availability in terms of what we can design and what we can make. And of course, the calculations that can be made through that. You don't have to have an entire pencil case full of different highlighters and colors if you're using a graphics tablet, because it's all there. It's all digital. And that's all through the software and the use of those ICs, integrated circuits. Another example would be the creation of the internet and social media and digital web conferencing, where in the past either a phone call or a physical meeting was necessary. Now a lot of that can be replaced with digital meetings, and I mean, we saw a really interesting example of this over our home learning period, when we had our pandemic. Um, the the home learning the home learning period was really aided by the ability to have conferences over Zoom, where digital lessons basically became the normalcy for a couple of years. So yeah, I mean, have a look at these examples. It's not required of you to memorize all of them, but it's just good to know sort of what the range is and how big that range is, because it is absolutely massive, the range of technology that's been developed through the use of integrated circuits. So I mentioned this already before, but we'll just go through it one more time. So I mean, the downsizing and the improved performance of the products is really what's been allowed by the development of ICs. So I mean, if you look at this example of this TV here, I mean, you've got an absolutely huge cabinet with a very small window, which is your TV, and then a big speaker down the bottom. Whereas, this 4K TV on the right here probably would have speakers on the back, or you might even have a sound bar underneath. But aside from the legs of the TV and the bezel itself, it almost looks like there's nothing there, because everything is overlaid behind this cabinet here, behind this physical screen here, which is where your circuit boards and stuff are going to go. So the ability to downsize everything using integrated circuits has really been the most useful thing in terms of developing technology. And I mean, another example here is, the use of thermionic valves was huge when we were using computers back in the day in the 50s. Um, but now, you can fit a MacBook in your hand, and the amount that your MacBook can process would probably be thousands of times more than what you would see in this image here. There's an interesting anecdote where the first spaceship that went to the moon had less processing power than your mobile phone by a factor of, I think it was like 10 or something like that, or 100. Um, but it's absolutely mind-boggling, really, to see the development in data processing and management for within just 50 to 70 years. It's been such a huge development. Okay, so we're going to look now at some new materials. Now, these materials are all quite varied, but the idea is for you to just get an idea of what materials are being used nowadays relative to sort of what was more common before, which were more sort of base materials. So glulam is actually pretty simple. It kind of, if you break it down, it's kind of self-explanatory because you've got glue and then you've got lam. So lam's short for laminating, and glue is short for, well, glue. And so the idea basically is you've got laminated pieces of timber that are quite literally just stuck together to create a kind of a thick section of wood, and you might see this quite often in Scandinavian structures. It's quite common in some other parts of Europe as well. But the idea is basically they're just timbers that have been glued, sheets of timber that have been glued together and laminated, and then cut out in specific shapes to create structural integrity. Very often for buildings, but it can be used for other things as well. And surprisingly enough, it does actually have a better strength to weight ratio than steel. So in a lot of cases, it is actually more useful. And also the fact that it's sustainable, because it's made out of wood, does give us that ability to build sustainably and to not go through our valuable resources, which we know we are eventually going to run out of. So we do want to try and preserve that as much as possible. Um, and then of course, because they are processed sheets of timber, you can minimize the natural defects in those sheets by not having to use every bit that is part of the tree. You can take, you can remove knots and you can remove sort of natural defects by selecting which pieces of timber you actually use, which then sort of improves or maximizes the structural integrity of the thing that you're building. All right, so let's look at the next one. Kevlar. Kevlar is something that you will probably know quite well. This was quite big in GCSE as well, so I'm not going to go too deep into it. But essentially, it is categorized as a polyamide, so it's polymers in chain form. So molecularly, they're chain linked together. It is an artificial fiber, and it's essentially woven fibers of carbon fiber that have been then sealed together chemically, and they're very often used for bulletproof vests, and also they're can sometimes used for puncture resistant tires. There's quite a big military application for it as well, just in terms of other fabrics and stuff like that. It does have an incredibly high tensile strength, and this is natural due to the natural structure, or well, it's not natural, but the inherent structure of the chemical bonding and the very dense atomic or molecular structure. Okay, um, moving on, we have PMC, which is precious metal clay. This is quite an interesting one. So what this is it's essentially clay that has precious metals suspended in it. We actually do have some at school. If you did want to make some little silver jewelry at school, you could actually do that. And the idea with this is basically you create the shape that you want out of your piece of clay, and then you heat it up. And what happens is the clay sort of melts away, and what you're left behind with is a little silver piece or a gold piece or whatever material is suspended in the clay. You're left with that with a little bit of shrinkage, about 10% shrinkage. So if you are making something that's made to fit, like a bangle or a ring or something, you do have to account for that 10%. Otherwise, it's not going to fit. So yeah, so this one's pretty simple, really. It is a kind of a mixed material because it does have clay, which is a ceramic, and then you do have precious metals in there as well. Now, nanomaterials is a bit of a generalized category, so I'm not going to go into the entire category of it. But for the most part, what you need to know is that nanomaterials are it involves the manipulation of materials on an atomic scale, which enables us to basically build these either new materials or edit existing materials with other properties by introducing other materials to it at an atomic level. Okay, a really good example of this is graphene. So graphene is essentially carbon atoms that are layered in a 2D plane. So it's literally one atom thick of carbon, and it's been discovered to have some really, really interesting properties. Um, there was a recent discovery, or maybe not so recent anymore, but if you were to drag saline solution, so salt solution, over graphene, you can actually create an electric charge. It wasn't really, at the time that I read this, I don't know what the actual development for that was or what the application for it was. But I mean, nanomaterials are such a new category of materials that there's so much still to be developed there. Um, and yeah, it's just a really interesting new sort of quote unquote species of material that's kind of been underexplored so far. Um, so there's quite a lot to be discovered there still. Now we're going to look at some methods of manufacture now. So we're going to start with electrohydraulic forming. There's a little diagram here for you, but essentially the idea is you've got a very high power uh, hydraulic introduction here, and then you've got a single-sided mold, which basically you're hydraulically pushing the metal into the mold, and that allows you to then create a product or create a shape or a form out of it. Yeah. Um, there's a little example in this video here. I recommend you to watch it. I don't think it's very long, but it's going to be nice to see sort of the actual process so that you get an idea of how it works and how it looks. Okay, we're going to look at SLS printing of metals here. So SLS is called selective laser sintering. Let me just check if I got that right. Selective laser sintering, yes. Um, the specific type of sintering is called direct metal laser sintering. But the idea basically is that you've got a powder that is set on a surface, and then you have a laser that goes along and it cures that powder, and then builds it layer by layer up into the actual object. So a lovely example here. This video on the left is quite a lot shorter than the one on the right, but if you do have time, I would recommend watching the one on the right because this is a very, very in-depth explanation of the process, which is quite useful to know, especially if you got an exam question that talks about processing materials in a very specific way or methods of producing a specific type of product or things like that. Okay. Um, Moving on here, injection molding of fibers. This one is actually quite interesting. I didn't know too much about this not until recently. So essentially, what this is it's a change to the existing standard injection molding process, where instead of pellets of plastic, it's pellets of glass or carbon fiber filled polymers like nylon are used instead. And the rest of the process is relatively similar, actually. The idea is you've just changed the material in the actual molding process. There are some slight changes that need to be made based on heat and production and things like that. But for the most part, it is kind of injection molding with a different material. This video here is a really nice example of how it looks. They go into a little bit more detail on the process itself. All right, and finally, laser beam welding and physical vapor deposition (PVD). Okay, so both of these link you to videos on how it works. So I recommend you to watch those. Basically, laser beam welding involves using an extremely high heat laser beam to join metals. And the benefit of this is that you don't have to worry about damaging the materials that you're welding to. So if I'm welding, sheet A to sheet B, I'm not worried too much about damaging the exterior of each sheet because obviously if you're using a normal weld like a TIG or MIG weld, the dispersion of heat is going to be greater, so you have to have quite a high level of skill to do it quite precisely. Whereas obviously if you're using a laser, it's a lot easier to be precise. Um, and it can also be quite a bit faster as well because lasers get quite a lot hotter. And it does actually let you weld quite deeper as well. You can actually weld deeper into the material, so you're causing a bond not only on the surface but several layers below. So that's another benefit of it. It can actually also be combined with MIG and TIG welding, so you can laser weld it first, and then for extra security, you can then MIG or TIG weld the surface of it, and that will then give you a very very strong connection. Okay. One of the issues with particularly laser-based products in general, even laser cutters have a problem like this, is that lasers require optics, and optics are just very small magnifying glasses or mirrors that move the laser around, focus the laser, bounce the laser from place to place, things like that. And the problem with that is those are very often either very shiny surfaces like metals or very clear surfaces like glass. And the problem with that is that the more it's used, the more it is exposed to things like dust, the more it's exposed to things like fumes, like smoke, or burning deposit from the actual metal, which will then create essentially like tar on the surface of the glass, or imperfections or impurities will stick to the glass. So it needs regular cleaning. And I mean, the laser cutters at school get cleaned quite regularly, and very often, if the laser cutter is not cutting through something, most of the time it's because the optics are a little bit dirty, so they need a clean. Um, the benefits of this, though, again, obviously, are the welds are really, really smooth. They don't need to be sanded down or filed down. If you've ever TIG or MIG welded before, you will know that if you like it to be very neat, not only do you need a very high level of skill to do the welding, but you actually also need to probably file or sand it down afterwards to really clean it up and make it look good. Yeah. Okay. Finally, we're going to look at CAD and CAM advancements. So CAD CAM advancements basically are just over the past 50 or so years, what has developed in terms of CAD CAM, how has CAD CAM improved, in what ways can we now use CAD CAM that we couldn't before. So I mean, there's a couple of really interesting ones. VR is a really big one, and I think VR is probably going to get a lot bigger in the future. My perspective on it is that I think VR is actually, in some cases, it's going to be better used for design than it is going to be for a lot of other things, because I think you probably need to have quite a bit better kit to really experience VR in terms of things like movies and gaming and stuff like that. Whereas with design work, there's not so much movement involved. There's not so much physical interaction. It's more of a visual interaction where you're kind of seeing a product, spinning it around, interacting with it in a more technical way where you're sort of making changes to it. So it's just a more useful and comfortable interface when you're looking at something in a 3D space. And it also allows you to feel things like scale. So actually, in architecture, VR is often used quite a lot because you can experience a building, but you can also experience a room, you can experience a hallway, a staircase, and you can really get a feel of what that's going to look like. Um, Integrated realization is just a fancy way of saying FEA and CFD, which you may already know from previous sections, but basically finite element analysis tells you things like stress and strain on different areas through sort of algorithms in the CAD software, and then CFD, which is computational fluid dynamics, basically lets you work with an object within a fluid to see how it reacts with things like atmospheric pressure and things like that. And of course, even just by natural air as well, like within in the air as well. If you're designing like an aircraft or something, because air is technically a fluid, right? Um, and then a slightly more simple one is actually just cloud-based CAD/CAM software. You may already know this, but back in the day, CDs were a big thing. You had to buy a software on a CD or sometimes a USB, and then you'd have to install it, which meant it was local to your device. Now, if I had to send this to somebody else, they would not be able to look at it unless they had the same software that I did. But now you've got things like standardized formats, so you've got STLs and you've got step files, and then you've also got DXFs for 2D files, which makes sending files to other people a lot easier. So it makes the collaborative work of design just so much better. And then further to that as well, some CAD softwares actually allow you to share your screen with people. So let's say for example, I designed something and I wanted to show it to my factory, I could send a link to my factory where they could then access on their web browser a really simple version of my CAD software with my file in it, so that they could spin it around and have a look at it and interact with it. And I mean, hopefully in the long run, maybe they could put on a pair of VR goggles and see it in VR and really get a feel for what they're looking at. Um, and then another quite interesting one as well is mass customization, which basically just is what a lot of brands do nowadays, where they allow you to sort of customize things that you buy online. Apple does this a lot, where you ask for an engraving or an inscription on something, or it might be something a little bit more in depth, like Nike, where you can choose colors, or I think you can also choose stitching and stuff like that. So it actually introduces a little bit of CAD input or design input from the customers and the clients, which does sort of on a per product basis, it does give quite a lot better sort of variation. Gives a lot of options to the buyers. Okay, and then social, moral, and ethical issues in regards to production in general. So industrialization has led to some really interesting issues, and I mean there are some of them which we're still looking to solve now. We're still looking at, what's the best way to approach this, and I mean I mean, although the Industrial Revolution was a while ago, we are still looking at the problems or the sort of issues that result from these really like big production facilities and the need to constantly be producing things. Um, so I mean, a really good example is just the introduction of machinery and automated manufacturing reduces low-skilled jobs and labor-intensive jobs, which I mean that naturally has its own issues because you have people who are trained in lower income jobs, and so their jobs will be much more simple, but then they've been replaced by machinery, and so they're left without a job. Um, but then that leads to the opening of other facilities which then do require labor, but then at the same time you're still using more resources for that. So there's an interesting dichotomy there to be had. Um, it is our responsibility though as designers to sort of bear in mind what the impacts are going to be of the work that we do. So, I mean, whether it's ethical, moral, environmental, it really is our responsibility to try and think about, how can we impact all of these in as little as possible of a way. Um, and I mean, it can be as simple as thinking about like, okay, well, where are we getting our materials from? Are we getting them locally? Are we getting them flown in from somewhere else? And if we are getting them flown in from somewhere else, can we get them locally instead? Because if we get them locally, we don't have to then worry about transport and all the fossil fuels going into the gasoline that's required to actually send the ship over here or send the plane over here or whatever it is. And I mean with very large amounts of material, you're talking about like containers and containers and containers worth of stuff, and I mean the amount of energy required to move that across the world is it can be a crazy amount. It can be a lot. Um, However, a lot of times the developments that we look at as negative, things like military developments are very often seen as negative because, um, well, because military implies conflict and conflict is bad. um, they do lead to some really interesting positive outcomes, positive products. So radar was a development of the military, as was EpiPens, as was drones, as was nylon, GPS. So again, that's another interesting sort of dichotomy to be had because through the need of development for military technology comes all these really interesting products and really useful products that do improve, our livelihood and humanity. But at the same time, um, they come from kind of a questionable source, right? Um, yeah, now looking at culturally acceptable and non-offensive products, this basically just implies knowing who you're designing for and knowing what you design and how it appeals to different cultures. So a really simple example of this would be, the use of black, particularly black fabrics in the context of events in the U.S. and UK implies sort of death and mourning, whereas in the East it represents wealth and prosperity and things like that. So, I mean, just being aware that, different countries and different cultures and religions perceive things differently, just even if it's in terms of colors or it's in terms of, the way things are presented, um, it can really affect how our products are perceived, you know. So using neutral colors and using neutral kind of tones and stuff like that, if you are designing something that is going to be questionable in that sense, is probably wise. Okay, so just wrapping up here with some key terms. Um, so the product life cycle obviously is the entire sort of stages of the product that it goes through from sort of introduction to decline and replacement, bearing in mind that decline and replacement also involves very often planned obsolescence and stuff like that. Socioeconomics, um, how the society and the economy interact to create, certain demographics and certain circumstances for which, as the designers, we need to be aware of. Rationing, we've been through this. Obviously, it's the shortage of goods or resources created by war or other crises. Utility products, basically post Second World War, um, products that were used for the purpose of utility, and were often rationed, so were often very low in availability. Council of Industrial Design. This is basically just an organization that was set up post Second World War to improve design standards and to improve competitiveness as well. Microelectronics is basically mini devices that have been facilitated by the development of integrated circuits. And again, integrated circuits basically being the use of transistors and small components and devices that have been created through the development of the IC that allow us to then shrink everything down and make products a lot more usable, a lot more handheld. And then finally, sort of sustainable and ethical and fair trade are sort of similar within the same category. So when it's sustainable, the idea is that it can be replaced or it is not finite, so it doesn't have a full-on limit. So an example of something that is finite would be maybe a precious metal. There's only so much precious metal in the world. Precious metal isn't being regenerated at any rate unless we went to another planet and found precious metals there and brought them back. But we're looking at particularly on our planet, right? Um, Ethical, basically looking at are we being morally fair to whoever it is that we're dealing with, whether it's to an individual, to a group, to a factory that we're working with. The idea is, being sort of fair and socially respectable to everyone that we work with. Fair trade essentially is just making sure that it is a movement, but it is quite widespread now. It encourages the ethical treatment of farmers and workers by paying them what their product is worth in our place in the world rather than in their place in the world, because that would be unfair to the work that they do, because it is being sold at our prices, and so they should be paid. That we should pass that advantage back to them, so that they can sort of further develop their lives. Culture, that one's a little bit of a self-explanatory one. I'm sure you know what culture is. Essentially, just the combined sort of or the growth of the way that we've lived over a very long time, and that is obviously passed from generation to generation, and that develops sort of who we are today and how we live today. And then finally, inclusivity is considering the entirety or the full range of everyone that could possibly use our product. So even if we're designing something for able people or mobile people, making sure that we are able to try and include as best as possible people who might not be as mobile, or who might still be able to use that product even if they weren't physically mobile in some way. That's basically the main concept there of inclusivity. Okay, that's pretty much it, guys. There's going to be some practice questions and Quizlet at the end for you as well. So have a go at that to check your knowledge out, and don't forget to watch those videos and flip through the textbook as well for a little bit more in-depth on any of these topics if you need a little bit more. Okay, thanks for watching.